Hey, what's up, Algebra 2? Today we're going to be going over exponential functions and how to graph them. Exponential functions come up a lot in science and math. It comes up in cell division, a lot in biology, and it comes up in banking and interest. And PERT, we'll get to all that later, but the main idea is exponential functions come up a lot in everyday life, so it's important that we understand them. Also, I'm going to talk sort of softly because I don't want to wake anybody up. I'm kind of recording this at night. Okay, so first thing I want to say is I want to make the distinction that quadratic functions and exponential functions are different. Quadratic functions are y equals x squared, and whereas exponential functions are y equals 2 to the x. Obviously, some variation of this is quadratic functions, and some variation of this is exponential. And so these are two drastically different things, so do not get them mixed up. Okay, so let's jump into this. We're asked to graph f of x equals 5 to the x power. The first thing we're asked to do is find where does this graph cross the y-axis. The y-axis is anything along this line. Oh, sorry, I forgot to erase some of this. Is anything along this line. And that's where x equals 0. Right, so let's plug in 0 for x. 5 to the 0th power is just going to be 1, right? So we have this point 0, 1. Sorry. Okay, let's put that right there. Okay. Now, what values of x does this function use? This question is getting at the domain of the function. So, what possible values for x can we plug in here? Can we plug in -1? Can we plug in -500? Can we plug in 0, 1, 500? Yeah, we can plug in any number we want, right? There's going to be no restrictions on the number we raise 5 to. So we're going to say all real numbers. Okay, what values of y does the function use? Now, this is saying the output, right? This is talking about the range. So when we plug in all of these numbers, all of the numbers, x values in our domain, what y values will that produce? So to do that, let's actually graph this first. So let's do 1, where x equals 1. 5 to the first power, right? We're just plugging it into this equation. 5 to the first power is just 5. So we plug that point in. Now for x equals 2, we have 5 to the second power, 5 squared. That's going to equal 25, right? And now what about negative? We said we have all real numbers, so let's raise 5 to the -1st power. Now if we go back to last unit, we know that we can just, any negative exponents we can put on the denominator. So 5 to -1st power is the same thing as saying 1 over 5 to the 1st power, right? Just 1/5. So let's put this somewhere like there. Okay, and now let's plug in -2. 5 to the -2nd power. It's going to be the same thing as putting it on the denominator and doing 1 over 5 squared. So 1 over 25. And that's really close to 0. So let's connect all these dots. I may not do the best job of this. Jeez, yeah, that's really bad, but you get the idea, right? It's increasing at an increasing rate. So what y values do we see in this function? This keeps on going, right? Well, all of our y values, if we look here, our y value is like 0.2 or 0.1 or something positive, but it's getting closer and closer to 0. If we pick a point here, we have like 10, right? Here it's 5. All of our y values our range is going to be greater than 0. So y is greater than 0, right? If we pick any point on this graph, our y value is going to be greater than 0. And we can see that on this graph, right? Now, one thing I want to say is this is not y is greater than or equal to 0. As we'll get into here in number D, when this left side keeps on going closer and closer to negative infinity, it's never going to reach 0. It's going to approach 0, but it's never going to actually reach it. So that's why we can't say y will ever equal 0, but it's always greater than 0. So what is that called? An asymptote. And you might remember that from last unit at y equals 0. Right along this line, it's never going to get to y equals 0. That's the main point. Okay, so let's scroll down here. Let's do some of these. Okay, so let's do y equals 2 to the x power. Something like that. Okay, y equals 2 to the x power. Y-intercept. Y-intercept is when x equals 0. So let's plug in 0 for x. We have 2 to the 0th power. Anything to the 0th power is just 1. 0, 1. Let's put that down here. Okay. Now, domain. Domain, we can raise 2 to any power we want. We can raise it to a negative power, positive. We can raise it to 0. So here it's also going to be all real numbers. Now our range, let's graph this to figure out our range. So if we let's plug in a couple of points. Let's say what happens when x equals 2. 2 to the second power is going to be 4. So let's put a point there. Let's say here, 2 to negative first power is 2. 2 to negative first power is 1 over 2 to the first power, which is just 1/2. Let's do there. And let's actually do one more point. 2 to the negative second power is 1 over 2 to the second power, which is 1 over 4, 1/4. Let's say something like that. Okay, and let's create a line from this. Okay, something like that. We probably could have added another point over here, but it's all right. We get the idea. And so what's our range of y values here? If we pick any point on this graph, our y value is going to be greater than 0, right? This is pretty much what we did with our problem right above. So we're going to say y is greater than 0. Okay, now where's the asymptote? Well, if we look at this, our y values are going to keep on approaching 0, but it's never going to get to 0, right? This is exactly like what we talked about in the problem before. So our asymptote is going to be at y equals 0. Okay, now let's switch this up. Okay, now let's do y equals 3 to the x power. So first let's find our y-intercept. That's when x equals 0, so 3 to the 0th power is just 1. So we're going to say 0, 1. Let's plot that point. And now we have our domain. Exact same scenario. All real numbers. We can raise 3 to any power we want. Range, let's plug in some points. Let's plug in 1. 3 to the first power is just 3, right? 3 to the third power is 27. We're not going to get there. 3 to the second power is 9. So we have that point there. And let's do another point here. 3 to the negative first power is 1 over 3 to the first power, which is just 1/3. Something like that. So let's connect these dots. Right. Oops. Okay, wait, that. I'm not the best at this. Okay. That should be good enough. And so if we look towards this is the exact same thing. If we pick any point on this graph, our y value is going to be greater than 0, right? So it's going to be the same scenario. Y is greater than 0. In asymptote, it's approaching 0 again. This is like the last two problems we did. So y equals 0. It's our asymptote. Now let's do this last one. This one's going to be a little bit different. Sorry. Okay, that should be good. Okay, so let's find our y-intercept. So y-intercept is when x equals 0. So we do 1/2 to the 0th power. Anything to the 0th power is just 1. So we're gonna, 0, 1 is gonna be our y-intercept. Let's plug that in right there. Okay, and now let's plug in 1. 1/2 to the first power is just 1/2. So we plot that point there. And we forgot to do the domain. Let's do that right now. What do you guys think it's going to be? Yeah, it's going to be all real numbers again. For all exponential functions, the domain is going to be all real numbers. So you can just put that down. You don't have to think about it. Okay, with the range, let's keep on going. Let's do 1/2 to the negative first power. Let's actually write this out. Let me zoom to the side. Okay, so 1/2 to negative first power is going to be the same thing as saying 1 over 1/2 to the positive first power, right? We're just moving it down. So 1/2, this is going to come out to be 1 over 1/2, right? Which is just the same thing as 2. Oops, my bad. Same thing as 2. So we can plug in that point here, right? Let's do this again. Let's do 1/2 to negative second power. 1/2 to the negative second power is going to be 1 over 1/2 to the second power, which is the same thing as saying 1 over 1/2 squared is going to be 1/4. So this is going to come out to be 4. Now we could keep on going. You know, we could figure out some of these other points, but let's just graph this. We have enough points to get an idea. Okay, this is really bad, but hopefully you guys get the idea of what this graph looks like. So let's look at our range. Our range, pick any point, point to any point on this graph, and find what the y value is. Every single one of them is going to be greater than 0. So we have y is greater than 0. Here, what is this graph approaching? It approaches 0, but it never gets to 0. So this is also going to be y equals 0. Okay, so let's just take a step back and analyze this. Let's take let's take y equals 2 to the x power. This is our our blue graph. In comparison with y equals 3 to the x power, it's a little less steep, right? Y equals 3 to the x is more steep. And if we look at this, we see that it's increasing by a factor of 3. It's tripling, whereas our y equals 2 to the x power is just doubling. So our green graph with the higher sort of base, like the number we're raising to the x power, that's going to be more steep. Now here we have y equals 1/2 to the x power, and that's sort of flipped around. Instead of increasing at an increasing rate like these other two, we're now decreasing at a decreasing rate, right? And this is because our b value, right? We'll get into this a little bit more later, but when we have this is trippy. Yeah. A times b to the x. This value inside, this b, is less than 1. So now it's decreasing. So just have that idea in your mind. We'll sort of build on that as we go through. Okay, so now we have this next problem. Let's do this again. Okay, so y equals 2 to the x. You can look at what we did before. Same thing. Y is greater than 0. Sorry, that's a y. And then y equals 0. And we can graph this again, right? Sorry. Okay. Right, same thing we did before. This is our graph. Now, let's look at this next one. Now we have this number out front. If you look at the equation I said before, y equals a b to the x. Now we have a 3 out in front. So let's see what that does. Let's plug in 0 for x to find the y-intercept. 2 to the 0th power is 1 always, and then we multiply by 3. So now we have 0, 3. That's really important. Can we still raise x to or 2 to any power we want? Yeah. So our domain is going to be all real numbers. And to find our range, let's just start plugging in points to get an idea. We said our y-intercept is 0, 3. So we have a point there. Let's plug in 1 for x. 2 to the first power is 2 times 3 is 6. Got that right there. X equals 2. When x equals 2, we're doing 2 to the second power. 2 squared equals 4, and then 4 times 3 is 12. So we have that point up there. And then let's plug in -1. 2 to the -1 power is equivalent to 1 over 2 to the first power, right? Which is just 1 over 2, 1/2. So we have something like, and then we multiply by 3, sorry. So 1/2 times 3 is 3 over 2, which is like 1.5, so something like right there. And then let's connect the dots, and we get something along those lines. And so if we pick any point on this graph, our y value is going to be greater than 0. So we have that right there. And just like before, this is approaching 0. It's never going to get to 0. It's an asymptote, but it's approaching 0. Let's do this last one. Y equals 1/2 times 2 to the x power. So to find the y-intercept, you know the deal. We plug in 0 for x. 2 to the 0th power is 1. 1 times 1/2 is 1/2. So our y-intercept is 0, 1/2. Okay, domain all real numbers. Any exponential functions can be all real numbers for domain. Now let's start plotting this to find our range. We have 0, 1/2. We start here. And then let's plug in 1 for x. 2 to the first power is 2 times 1/2. That's 1. Oh, sorry. This. Ooh, I don't know if I can go back. Disregard that. This point is actually down here. Sorry about that. When we plug in 1 for x, we get 2 to the first power. 2 times 1/2 is 1. So there we have 1. Sorry. I don't want to like erase it, then I'll erase the entire graph. Okay, so when x equals 2, we have 2 to the second power. 4 times 1/2 is 2. Sorry, for some reason. Yeah, nah, this is trippy. I'm sorry. Yeah, this is bugging. Okay, now let's do 2 to the third power is 2 cubed. 8 times 1/2, 4. Right, so hopefully you can start to see this graph here, right? Okay. So what's a range? Same deal. Y is greater than 0. And it approaches y equals 0, right? It's approaching this x-axis, but never actually touching it. Okay, so let's notice some patterns. We're changing the number out in front, right? Whatever we're multiplying this 2 to the x by. Here we have sort of like an invisible 1. Here we're multiplying by 3, and here we're multiplying by 1/2. Let's look at our y-intercept. It's changing our y-intercept here, where we have y equals 3 times 2 to the x power. Our y-intercept is 0, 3, right? Here where it's 1/2, our y-intercept is 0, 1/2. Here it's 0, 1, right? We have an invisible 1. So it's sort of changing our y-intercept. That's what the number out in front of this does. That's important. Okay. Let's move on to this one. Okay, so y equals 2 to the x power plus 1. So we find the y-intercept by plugging 0 in for x. 2 to the 0th power is 1, and then 1 plus 1 is 2. So our y-intercept is 0, 2. Domain, all real numbers. Range, let's start plotting this and then we'll get our range. So we said our y-intercept is 0, 2. Let's plug in 1 for x. 2 to the first power is 2. 2 plus 1 is 3. So we graph that right here. When x equals 2, we have 2 to the second power, 2 squared, 4. 4 plus 1 is 5. Let's do 3 just for good measure. 2 to the third power is, 8. 8 plus 1 is 9. So something like that. And for the negatives, we have 2 to the negative first power. 2 is equal to 1 over 2 to the first power, which is 1/2. And then we do plus 1. That brings us to 1.5. And let's plug in negative 2. 2 to negative second power is 1 over 2 squared, which is 1 over 4. So 0.25 plus 1, 1.25. Something like that. It isn't going to be the most exact. Let's connect these dots. And as we keep on going, well, actually, I'll explain that in a second. Okay. So as we keep on going, right, if we have 2 to the x, before we said 2 to the x, if we look at our graphs before, it's approaching 0, but it will never get to 0, right? So we can go to -8 and we'll get something super small, but it's never 0. So when we add that to 1, it's going to be something, as we go to negative, we're going to get close to 1, but we're never going to actually reach 1. So if we look at any point on this graph, if we point to any point, what's our y value? Here it's 8. Here it's 2. Here it's like super close to 1/2, but it isn't 1/2. Or sorry, super close to 1, but it isn't 1. My bad. So our range is going to be y is greater than 1. Okay. And right, just find range by pointing to all points on the graph, and you'll see a trend. You'll see what it's greater than or less than. And so our asymptote, what are we approaching? We're approaching this line, y equals 1. This is going to be super hard, but if we create almost like a dotted line across here, I'm not going to actually draw it, but if we create a dotted line across here, it's going to approach it, but it's never going to actually reach it. And so that's what we define an asymptote as. Okay, let's do this real quick. Y-intercept x equals 0, 2 to the 0th power is 1, 1 minus 3 is -2. So we have 0, 0, -2. Domain, all real numbers. Range, let's plot this. We have -2 as our y-intercept. And then let's plug in 1, 2 to the first power is 2 minus 3, -1 right here. And let's do 2 squared, minus 3 is 1, so we have something like that. Let's plug in -1, 2 to negative first power is going to be 1/2, minus 3 is -2.5, so something like that. And we can keep on plugging in points, but we're going to get a graph that eventually looks something like this. Something along those lines. And so what's our range? We point to every single point on this line. We'll see that they're all greater than -3. Y is greater than -3. And so that's our range of our y values. And what is this approaching? As we move to the left, it's getting closer and closer to -3, but it's never actually reaching -3. And we'll do an overall analysis of this, with these graphs and why it's like that in a second. Okay, here we have something different. In our exponent, we have x minus 1. So x, our y-intercept is when x equals 0. So we plug in 0 for x, and we have 2 to the 0 minus 1 power, 2 to the negative first power. And as we've gone over before, that's the same thing as saying 1 over 2 to the first power, so just 1/2. Range, all real numbers. So let's put this in. We have 1/2 here. Boom. And if we plug in 1 for x, we have 2 to the 0th power, which is just 1, right? If we plug in 3 for x, we have 3 minus 1, 2. 2 squared is going to be 4. So we'll get eventually a line that looks, or actually let's plug in -1 just for good measure. -1 minus 1 is -2. 2 to the negative second power is the same thing as saying 2 or 1 over 2 squared, which is just the same thing as saying 1/4. So we have something that maybe looks something like that. Okay, so eventually we get a graph that looks like this. And we point at all values on this graph, and we see that they're all greater than 0. Sorry, did I say, ooh, wow, my bad. I'm sorry, y'all. this is supposed to, whoa, this is supposed to be -3. I don't know why I wrote something different. My bad. Okay, so here are all of our y values are greater than 0. So we say y is greater than 0. And if we look at what this graph is approaching, it's approaching our x-axis, which is just y equals 0. Okay, so what are some patterns we notice? Let's compare this first equation to this second equation. The only thing we're changing here is what we're adding on at the very end. If we look, this is pretty much the same graph. This blue and black graph is the same graph, except we're vertically shifting it. This is vertically shifted up 1, and this is vertically shifted down 3. So that's what this constant added on the end does, the effect it has on our exponential function. Here we're raising it to a power, but now we're subtracting 1. And if you see here, if we compare this to our 2 to the x functions, or regular 2 to the x functions, and you guys can plot this on Desmos and see, now we're horizontally shifting this exponential function. So when we have x minus 1, we're shifting it 1 in the horizontal direction to the right, I believe. Right? This 1 here, if it was just 2 to the x, it would be here. Everything would be shifted. Everything shifted to the right now here. But if we were to revert it back to just 2 to the x, everything would be shifted to the left. I don't know if that makes sense. If you graph it on Desmos, you'll get the idea. Basically, what you should know is this value, these values, are vertically shifting this exponential functions, whereas if you're affecting our exponent, now we're horizontally shifting our function. Okay, so let's analyze that real quick. I'm sorry, this is, yeah, so I'm not the best with tech. Oh Lord. Okay. Yeah, I don't really know what's happening here. Okay. Let's see. Okay, here. We just talked about this. This, our k value, is vertically shifting. Vertically shifting. Just gonna say vertically shift. Here, we just talked about this h value, horizontal shift, horizontal shift. Okay. And notice that it's in the opposite direction. So when we're subtracting something, we're moving to the right. And if we're adding something, we're moving to the left. It's the same thing if we remember vertex form of parabolas. It's sort of like that. Transformations have similarities between them, even though these functions like this looks entirely different than a rational function, but some of these same principles apply. If we look at this b value, I don't know if I'm going to be able to, you get the idea. That's our b value. That's going to affect our growth / decay rate. So how steep our line is. And this, our a value, this is affecting our y-intercept. Now, it's not like you can look at A and say, hey, that's our y-intercept. There's also, if we vertically shift things, that's going to affect it. So yeah, don't just see, hey, A, and then plug that in as your y-intercept. Plug in 0 for x and you can find it out relatively easily. Yeah, okay. So let's check our understanding. A function that triples and goes through the point 0, 5. So you have a function f of x. Triples. Here, that's referring to our growth / decay rate. So our b value should be 3. Let's write that here. 3. We want it to triple. We're multiplying by 3 every single time. So 3 to the x. Now it goes through the point 0, 5. Now you could do this two ways. I suppose you could actually horizontally shift it, but that'd get really weird and you get some crazy decimal. But you could vertically shift it up 5, so you could add 5. Or we could have 5 on the outside here, and that's what I'm going to do. Yeah, that's what I'd recommend. There's a bunch of different ways, but yeah, this is our function. It triples because our b value is 3. It goes to the point 0, 5 because our a value outside is 5. And right, if we plug 0 in for x, we'll get 5 as y value, so that satisfies that. Now we want to asymptote at y equals 4. If we look up here, we changed our asymptote, right? We changed our asymptote here by adding constants at the end of our equations. So let's do that. We have, let's do f of x equals 5 times 3 to the x power plus 4. Now, any point we plug in here is going to, be greater than 4, right? If we just take this exponential function, our range is going to be y is greater than 0. So when we add 4 to that, now our range is going to be y is greater than 4. We're vertically shifting it up, and therefore we're vertically shifting our asymptote from y equals 0 to y equals 4. And a little side note here, this no longer goes through the point 0, 5. It would go through the point 0, 9 instead, but I don't think that's what they're trying to get at with this question. They just want you to know that vertically shifting will change your asymptote. Okay, so we're given this sequence, 20, 9, 4.05, and then 1.8225. It just keeps on going. So this models an exponential function, and so we're going to try to find out what equation this represents. So let's write down f of x. So here we could say 20 is our first value, n equals 1, and then 9 is our second value, so n equals 2. But I'm actually just going to say, I'm going to zoom in a little bit. I'm going to say this is 0. My bad. This is 1. This is 2. This is 3. So we could say this is our first value, n equals 1, but we're not in this case. Either works. So for here, what's our growth rate, or what's our decay rate? This is getting smaller each time. So what do we have to multiply 20 by to get to 9? 20 times x equals 9. If we just do some simple algebra, divide both sides by 20, we get 9 over 20. Now, let's do this again. Let's multiply, hey, if this is our decay rate, 9 over 20, if we multiply 9 times 9 over 20, you can barely read that, but it's all right. You guys can hear. We should hypothetically get 4.05, which makes sense because we'll have 81 over 20. So we get 4 and then 1/20. So we could do that again. If you bring out your calculators and multiply 4.05 by 9 over 20, you should get 1.8225. So this is our growth rate. This is our decay rate. 9 over 20 to the x power. You could also use the decimal. Now here since this first value, this 20, I said it was our starting value, r is 0. When we plug in 0 for x, we should get 20. But right now, as we have the equation, we have 9 over 20 to the 0th power. That's just going to be 1. That isn't what our equation says. So if we scroll back up, right, we change our y-intercept, our starting value, by multiplying by a out front. So let's do that. Let's multiply by 20. And now, does that work? Well, if we plug in 0, it's always helpful on tests. Check your answers. Algebra is one of those maths where you can know if you have the right answer by just plugging it in at the very end and checking your answer. So let's plug in 0 for x. 9 over 20 to the 0th power is just 1. 1 times 20 is 20. So that first value is good. If we look at this second value, 9 over 20 to the first power is 9 over 20 times 20 is 9. Okay, perfect. If we have 9 over 20 squared, we'll have we'll get some number. I don't have my calculator out, but hypothetically, do it with your calculator. You multiply that number by 20 and you'll get 4.05. So this is our exponential equation, and let's graph this. Okay. So let's actually use that pattern that they gave us. We have that point 0.20. Now we have this point 1.9. We have this point 2, 4.05. Something like that. We have this point 3, 1.8. It's going to be something like that. I want to say something like that. Let's connect the dots. Sorry. Yeah. We're going to get something like that. Our y-intercept is when x equals 0. We said that was going to be 0/20th. Our domain, as with all exponential functions, is all real numbers. Our range, if we point at any point on this graph, our y value is going to be greater than 0. Our asymptote is, y equals 0. It approaches 0. Okay, hopefully that helps. If you have any questions, use your resources, consult the internet, search things up, use YouTube, ask your peers, your classmates, ask Mr. Whitaker. You can come to me, go to the tutoring center. You have a multitude of resources at your disposal, and my advice would just be to use them. Yeah, thank you. Have a good day.